Open the antikythera mechanism, and you not staring at myth 2. Rereading an engineering brief from ancient Greece. Call it what it is, an analog computer, an astronomical calculator with bronze gears, cut to model real cycles in the sky. It didn't guess the heavens. It computed them, turning hand motion into coordinated pointers that track sun, moon, calendar, eclipses, and according to Inscriptions more. If you care about the history of science and Greek engineering, this is the artifact where theory meets teeth counts. Start with the problem it solves. Calendars drift unless you reconcile the lunar month with the solar year. Festivals, agriculture, and navigation all depend on predicting cycles. The antikythera device encodes those cycles mechanically, so a single turn on a driving knob advances an entire astronomical instrument in step. That SY antikythera mechanism explained is really how to turn arithmetic into gear ratios. Front face first. Think of a circular dial with the zodiac and a civil calendar ring. One pointer marks the sun's progress through the zodiac. A second pointer for the moon carries a little black-white ball that phases from new to full. That lunar phase ball, ISNT decorative it, is slave to a gear train that models the moon's irregular speed using an epicyclic gear train with a pine slot device. As the moon's pointer moves, the phase indicator turns to match what the sky will show, making the instrument a compact astronomy tool, not a toy. Why an epicyclic train with pine? Because the moon doesn't move at a constant speed. Ancient astronomers knew its anomaly faster near one part of its orbit, slower in another. The mechanism builds that variable speed directly into the gears. A small pin riding in a slotted gear forces subtle speeding and slowing each turn. You're watching geometry approximate celestial mechanics with remarkable economy pure Greek technology, centuries ahead of medieval clocks. Now flip to the back to see the production dashboard of the cosmos. Two big spiral dials dominate, the upper Metonic dial for a 19-year lunisolar cycle, and the lower Saros dial for a repeating eclipse cycle of 223 months. Tiny subsidiary dials nest within. The ecliptic dial accumulates Metonic cycles, the exeligmos dial refines eclipse timing across triples of Saros cycles. A game's Olympiad dial tracks the cycle of major athletic festivals. Each dial is a calendar of motion. You set a date on the front, and the back tells you which month in a long cycle UVA reached and when eclipses are likely. Eclipse prediction on this instrument isn't magic. It's statistics embedded in bronze. Along the Saros spiral, small glyphs mark which months can host a solar or lunar eclipse, with notes on where in the day the shadow is expected. Advance the main drive and the pointer walks those months. You can read out an eclipse season years in advance without tables. It's Shipwreck archaeology delivering a working forecast board, driven only by gear. How did we learn all this from corroded fragments? High-energy imaging cracked the case. X-ray computed tomography and reflectance scanning red gear, teeth buried in bronze and inscriptions hidden beneath encrustation. Tomography separated overlapping layers, so researchers could count teeth precisely and reconstruct gear trains. Imaging also revealed thousands of tiny Greek characters, the device's own user manual. Without CT, the gear counts and inscriptions would remain guesses. With CT, you can audit the math. What about the planets did? The front display all 5 known to antiquity. Inscriptions speak of the sun, moon, and the 5 wanderers, giving specific period relations that would require additional gearing on the front. A recent model proposes a compact set of indirect epicyclic trains with pine slot devices to generate the complex planetary motions described in the text while staying within the physical constraints of the case. Not every scholar agrees on the exact layout, but the inscriptional evidence and feasible gearing show that a full cosmos display was intended. Inside the case, bronze gears are cut with hand tools but disciplined by number theory. A tooth count isn't random, it embodies ratios. Lunar months per year, months per cycle, cycles per long cycle. Stack those ratios in trains, and the output pointers land where astronomy says they should phase to phase, node to node, season to season. This is why the device remains a benchmark in Greek engineering. It's careful math and metal. Zoom in on the lunar system to see the craftsmanship. A train feeds a differential that produces mean and anomalistic components of lunar motion. Then the pine slot imposes variable speed, and the phase ball is geared to the sun-moon angular difference. One hand turn updates position and illumination together, so the phase you read on the front is physically coupled to the sky geometry. For an astronomy instrument made of bronze, that unity is the win. Fewer setting errors, more coherence in what the user sees. Back dials or spiral registers, each turn of the spiral subdivided by fine tick marks and labels. The Metonic spiral has 235-month boxers. The Saros spiral has 223. Pointers with tiny sliders or follower pins ride those tracks, and inscriptions in each segment annotate what to expect: calendrical names, eclipse notelets, and correction cues. It's a mechanical notebook that never forgets where you are in long cycles. A persistent misconception is that ancient artifacts were symbolic rather than functional. Here function is inscribed. The text clarifies how displays should look and what periods to use. C, T read letters match the gearing. Shipwreck archaeology didn't just recover a relic. It recovered documentation confirming intended outputs. When engineering and epigraphy agree, confidence in the reconstruction spikes. So how do you operate it? Set the calendar ring to match your civil months? Engage the hand crank to step forward. Watch the front pointers advance along the zodiac while the phase ball turns. Flip the case to check the Metonic month for ritual timing or agriculture, then scan the Saros track for eclipse months. If an eclipse month lands, the tiny note near that cell tells you what kind solar or lunar and guidance on timing, refined by the exeligmos pointer. Mechanically, it's small, but conceptually, it's a system. Gears translate uniform hand motion into different angular speeds. Epicyclic carriers create compound motions. Pine and slot couplers inject periodic inequality. Every display is coordinated, so you don't manage separate tables. You turn one input and many outputs cohere. That integration is what makes it an astronomical calculator rather than a bundle of dials. Place it in context and it gets bigger, not smaller. Greek astronomy had robust geometric models for sun, moon, and planets. Craftspeople knew how to cut wheels and axles with tight tolerances. Scholars knew the right periods to encode. The antikythera mechanism is where those streams meet. Greek technology, astronomy instrument, an analog computer, and a wooden box. It's also a message about information design, complex cycles made legible through layered dials. What did the device not do? It didn't discover eclipses, it scheduled them. It didn't show realistic star maps. It indexed a parapegma-style calendar around the ecliptic. It didn't run itself. A human drove it, read it, and used the output for ritual, planning, or teaching. Knowing the limits makes the achievements sharper. Where does research stand now? Imaging keeps improving reconstructions. Epigraphers continue to read faint characters. Mechanical historians test alternative trains that satisfy both space and inscription constraints. There's active debate about the exact planetary display configuration on the front, but the lunar solar calendar and eclipse subsystems are robustly decoded. As more fragments and readings are integrated, models converge on a consistent cosmos display that fits within the known case geometry. If you're scripting visuals, here's the production checklist. Open with the corroded fragments, then cross-dissolve to a clean rendering that labels the front zodiac and calendar rings. Cut to the lunar phase ball and animate the pin and slot. Speed change, use a side schematic to show the pin sliding in the slot across the carrier. Flip to the back and track along the Metonic and Saros spirals with a macro camera move. Land on a single eclipse glyph to explain how prediction is encoded. End with the inscription panel that mentions planetary periods. Then overlay the proposed front-face planet pointers to show how inscriptions drive design. What does it change in our story of innovation? It erases the gap between pure theory and applied mechanism in ancient Greece. It shows a culture able to translate abstract cycles into gear networks and to package them as portable knowledge. It reframes ancient artifacts as engineered instruments, not curios. And it sets a bar. If you want to claim a technology, build it so it computes. The cleanest takeaway for viewers is simple. The antikythera mechanism is a geared model of the heavens that integrates lunar phases, lunisolar calendars, and eclipse prediction with inscription-driven evidence for planetary displays. Its core tricks are epicyclic gearing and a pine and slot coupler that mimics the moon's variable speed. We know this not by guesswork but by tomography, tooth counts, and thousands of recovered letters. That is what makes it the benchmark analog computer of antiquity and why it's still teaching us how to turn sky math into metal. If this evidence first tour delivered clarity, stay with the channel. Next, we'll unpack how tooth counts encode period ratios and build a working epicyclic demo you can understand at a glance.